So today I'll be talking about trying to get a more fundamental understanding of what's going on inside neural networks during training and afterwards, and how that can be useful. In the end, I'll talk about how that can be useful for applications in physics and otherwise. So we have a lot of unexplained phenomena in deep learning that we don't quite understand. And we all know that the pace of innovation in deep learning is not bottlenecked at all by the theories that help to explain it. So there's a huge disconnect in terms of, theoretically speaking, understanding the architectures, learning algorithms, and all the tricks that we use. I classify these issues into four main categories. Parametrization is the first one. Turns out that you need to overparametrize neural networks, meaning you need way more parameters, way more width in the networks than are actually required for the resulting functions that are learned. So if you take a neural network, make it extremely wide, train it, and then take the learned function and prune the parameters, you can many times reduce the parameters by 90, 95%. That's a 20-fold reduction and not lose any accuracy in your resulting function, training or test. So that tells us that that overparametrization, which seems to be necessary for training, is not necessary for expressivity. Another mystery involves the so-called lottery ticket hypothesis. When we use random initializations in our very wide overparametrized networks. However, it turns out that a very small subset of the parameters in those initializations are actually critical or relevant for the final fitting. This is known as the lottery ticket hypothesis, and some basic explanations have been proposed, but to date, there is no satisfying theoretical explanation. The lottery being that if you have enough parameters, that some subset of them will be good, where good is not well defined, but basically means that training works. Some issues with loss surface understanding. So the loss surface of deep learning is highly non-convex due to the nonlinearities in the hidden layers in the activation functions. And yet, despite this heavy non-convexity, it turns out that so many local minima end up being close to the global minima. Right? So what is that all about? And the final class of mysteries is relate to generalization. There are a variety of mysteries, but one in particular that has caught my group's interest is this notion of implicit regularization of the optimization algorithm. It turns out that whether you use SGD or ATOM or batch norm SGD, it might all sound like different variants of the same optimization algorithm, but the resulting solutions that you gain from the algorithms have different generalization properties. And in particular, Nathan Cerebro's group has shown this. So if there is some regularization going on, some smoothing that's critical for your generalization error to be low, it's implicit in the algorithm, and we need to understand it, make it explicit, and maybe even exploit whatever's going on. So these are the kind of big issues in the theory of deep learning that theorists are working hard at. And one potential solution, which I'm not the first to propose this, but one potential solution to this problem is to try to get away from weights and biases and go back to function space. Now, what do I mean by going to function space? Well, first, let me tell you about a little related work in that area. So this function space idea is kind of emerging across multiple research labs. Simon Du and Sanjeev Arora at CMU and Princeton have done a lot of work recently to understand, instead of worrying about how the weights and biases change during training, instead worrying about how the predictions of the network on the training data change. So modeling the dynamics of the output predictions over the training data over learning, rather than the weights and biases. And that has led to some interesting results that weren't possible otherwise. Behnam Neshaber, Nathan Cerebro, and others have shown that this implicit regularization phenomena seems to be not just specific to deep learning, but actually happens in all machine learning problems where you have, or in many machine learning problems where the loss function and the optimization problem is highly underdetermined. So I think, in the deep learning setting, I think you have so many parameters that you should easily be able to interpolate the data, right? If you can do that, then there's a lot of freedom as to what happens between the data points. but this seems to be a general phenomenon. And it turns out that according to their work, that the parameterization of your network or your machine learning model can make a big difference in combination with your learning algorithm in those regions in between the data. So this is, remember, this is not about the loss function. The loss function could care less what happens in between the training data. And finally, some work from a colleague, my postdoc mentor, and a colleague of mine at Rice, Rich Bernick's group, has also been pushing the spline perspective. They have some nice recent papers in ICML, ICLR, trying to understand the high-dimensional geometry of the polytopes induced by a deep network. So very, very interesting discussions going on in these fields. Okay, so let's go to function space. What do I mean by function space? So that wasn't supposed to run, but anyways. So in function space, what does it look like? Well, basically, let's take a very simple example of a neural network, just a one hidden layer, univariate shallow ReLu network. That means I have one affine transformation, I have a ReLu, and I have a linear layer at the end. So this is in the weights and biases parameterization, the traditional parameterization of a neural network. Now, via some algebra, you can rewrite this in the following way in terms of a so-called breakpoint slope parameterization or spline parameterization. Now you have these mu sub i's and these beta sub i's. These beta sub i's are so-called breakpoints. They refer to, because you know that this is a piecewise linear function, and so if you want to understand the pieces, you need, you basically have, right? So these are the breakpoints pieces, and they're also referred to in the spline literature as knots. So these are the x coordinates of these breakpoints or breakpoints for short. These are the beta parameters here. The other interesting parameter is these mu sub i's. We call them either delta slopes or discrete curvatures. What they do is they basically tell you, as you move from left to right, what is the change in slope. So if this is the effective slope here, and this is the effective slope here, then mu2 would tell you how that slope changes as you go from left to right. And in high dimensions, of course, it's a bit more complicated. But so this new parameterization is in terms of these discrete curvatures, these mu sub i's, or equivalently delta slopes, and these breakpoints. And of course, there's a third parameterization, which I won't talk about as much, but this is the traditional piecewise linear parameterization, where you literally talk about the effective slope and the effective bias in each piece, right? But we have a continuous piecewise linear approximation, and so this will be the better parameterization for us, because continuity is manifest here. Okay, so this is the basic, and the visualization we'll use throughout the talk is these little vertical bars will denote the breakpoints, or the knots. The color will denote their orientation, which I didn't mention, but basically each breakpoint has an orientation. It cares about either the right half space or the left half space. You can literally think of the breakpoints as little agents who have an orientation, and if an agent is facing this way, then his dynamics is only a function of that right half space. And conversely, if his orientation is the opposite, then he only cares about his left half space. So this is not, orientation is actually very important inside deep ReLu networks. It's non-standard in the sense that traditional splines do not have this notion of orientation. Okay, so these are the three different parameterizations of interest. We will focus mostly on the neural network parameterization and this breakpoint delta slope or BDSO parameterization. Yep, there you go. Important note is that, what are the role of these breakpoints? Well, if your function was affine, you wouldn't need breakpoints at all. So when you have curvature in your ground truth function, that's where you need breakpoints, right? The more curvature you have, the more second derivative you have, the more breakpoints you need. So we should expect that, as you see at the end of the simulation here, we see that the breakpoints start to congregate near the area of highest curvature because the rest of this curve is pretty straight. Okay, so let's talk about random initializations. So we all use the standard deep learning initializations, the Gloro-Bengio initialization or the Kaiming-He initialization. These are defaults in PyTorch, TensorFlow. And they're very simple. They're basically zero mean Gaussians for the weights and biases. However, what do they mean in the function space? In particular, a simple Gaussian distribution in weights and biases need not be simple in this parameterization. So what is the induced density and the breakpoints, the orientations, and the delta slopes? Oh, there you go. So it turns out that that very simple question requires a lot of math just to figure out what the answer is. And the resulting answer is quite simple, but it wasn't obvious to us ahead of time. So it turns out that there's a non-trivial correlation, even when you randomly initialize a neural network with Glorot or the Kai-Ming-He initialization, there is a non-trivial correlation between the breakpoint density, the breakpoint locations on the x-axis, and these curvatures on the y-axis here. So this non-trivial joint density means that as you consider breakpoint locations further and further away from the origin, the curvature drops drastically to 0. What that means is that there are lots of breakpoints near the origin. You can model curvature very well near the origin, but if you have non-trivial boundary conditions, which in many physical applications obviously you do, you're going to have a scarcity of breakpoints where you need them. So the initialization is not really suited to many kinds of physical applications where you may have a potential well, you might say it's quadratic here away from the origin at some length scale. This is a very bad init for doing that. So you better hope that your optimization algorithm can fix that by moving these breakpoints around. But then the question becomes how much can your optimization algorithm really move the breakpoints, and how much of its effort and computational cost is devoted to moving these breakpoints? If you knew this ahead of time, and in physics we have lots of prior knowledge, if you knew this ahead of time, you could have initialized your breakpoints in a much better density that reflects your prior knowledge. Yes?
But both of them have not only normal but also uniform distribution, so you can do CAD.
Yes. So the uniform distribution, so I didn't show those results here. We also have computed the distributions there. The same kinds of non-trivial correlations exist, even for the uniform distribution. So remember, it's not uniform in the breakpoint on the x-axis, it's uniform in the weights and biases. Yeah. So again, in physics, unlike in training on ImageNet, we don't know very much about the ground truth function of ImageNet images mapped to objects. However, in physics, we know a lot about the ground truth function. We are constrained by symmetries, by conservation laws, by lots of physical intuitions. We know a lot, and just kind of using a blind random initialization like this could be a bad choice. If you take the marginals of these densities, you find that indeed you get these kind of sparse distributions. So the density of the breakpoints in particular, if you look at the x location of the breakpoints, the density drops off as a Cauchy distribution. So inverse square law, it's a Cauchy distribution relative to the origin. So most of the breakpoints are sitting near the origin at initialization. That may or may not be appropriate for your problem. It's a comparison between theory and experiment there. Similarly, for the curvatures, these discrete curvatures or delta slopes, also highly, highly peaked at 0. What that means is that the initial function has extremely low curvature. It's very, very flat. And it's described by a MyRG function, which ends up being a modified Bessel function. The reason I mention this is because last time I saw Bessel functions was when I used to do physics problems. And I was just doing some simple machine learning thing, and this Bessel function came out of nowhere. So anyways, it was just kind of funny. So you can see that they're extremely peaked at the origin, and controlling just how smooth, right? If you want to control the smoothness, you can see here as a function of the standard deviation of the weights in the first hidden layer and the second hidden layer, you can control that distribution. But if you want to change the distribution fundamentally, you have to kind of think harder about what to do there. So later I'll show that these initializations really do matter. When we get to the gradient descent dynamics section, I'll show that initialization matters quite a bit. Okay, let's move on to the loss surface now. So as many folks know, there are a lot of degeneracies in the neural network loss surface, right? So for whether you choose mean squared error, cross entropy, whatever your loss criterion is, there are a lot of degeneracies, and the core reason for these degeneracies is actually quite similar to one of the earlier talks today. It turns out that neural network parameters, weights and biases, are highly degenerate themselves. You can think of it like a gauge group, in the sense that gauge degrees of freedom are unphysical. In the same way, a lot of weights and biases degrees of freedom are unfunctional, meaning that there exists an entire group of symmetry transformations. You give me a neural network, I will apply a transformation to the weights and biases, and it will leave the function unchanged. And the group that describes these transformations is actually very large. The volume of this group it's a continuous group and is very large. The simplest one subgroup to understand is permutations. We all know that if we permute the hidden layer of a neural network, it shouldn't make any difference to the function, right? But there's also a non-trivial group on the weights of each layer. You can scale up the weights and scale down the weights in certain ways that they compensate for each other and leave the function unchanged. So these sort of gauge degrees of freedom, ideally, they're there when we're training, right? When we differentiate, when we take gradients with respect to the weights and biases, they're always there. But what we care about at the end of the day, what the loss cares about at the end of the day, is the function, right? Not the weights and biases. So what we'd like to do is go from the neural network parameters and then basically fix or mod out this gauge group or this degeneracy group, and that gets us back to these parameters. So this is another way of motivating this reparametrization. By the way, this mapping is many to one. There are many, of course, that come here, but you can invert it. You can kind of choose a particular canonical scale for the weights and biases in a neural network so that you can kind of pseudo-invert it in a meaningful way. And one thing that's come out from our work is that actually in many optimizations, both for training and for probing, you have to go back and forth between these two spaces. Some things are much more easily done in this space, so you need fast, approximate, or exact algorithms for going back and forth between these, which we are currently working on. Okay, so why are there so many bad local minima in these laws? So even if you mod out, by the way, even if you mod out by these degeneracies, there are still many bad local minima, right? That's what we found. And we're working on theories to kind of understand what all these bad local minima are. But showing you some simple examples, we see that even when you just have 10 data points, right? On the x-axis here's n, the number of data points, and the different curves are for different numbers of hidden units. Even then, you start to see it's a sub-exponential lower bound, but you start to see a very high degree polynomial in n and h number of local minima. And
how are you defining bad?
Bad meaning that they're not global minima. Yeah, meaning that your optimization, if you initialize gradient descent, you can fall into that local minima and not achieve a training loss of 0 if a training loss of 0 is possible, right? So the theory is still developing here. This is ongoing work, but we did some empirical lower bounding just to get a sense of how bad is this? Is it exponential? It's at least it's at least polynomial, a high degree polynomial. It may be exponential in n and h. This is still ongoing work, so I don't have more to tell you there, but I will give you intuitions later on in the overparametrized case of what these loss surfaces look like. So let's consider now the overparametrized regime, right? So as we increase the width of a neural network, you fix the amount of data, training data, and increase the width, what happens to the loss surface? Well, recent work has shown that, so from Simon Du and Sanjeev Arora's labs, they've shown that a massively overparametrized deep neural network or shallow neural network can achieve a training loss of 0. It can achieve a global minimum of 0. Intuitively not surprising because you have enough degrees of freedom to fit the data. However, the proofs that they used to show that randomly initialized gradient descent will actually converge to this, you run into all kinds of really hairy issues along the way, right? So even though it's intuitive, showing that gradient descent will get there is highly non-intuitive. And the key trick that Simon Du used in his first paper was to basically say, I can't model the dynamics of the weights and biases. It's too hard to understand. Let me model the function outputs. Let me model the predictions instead and how they change over learning time. So that was kind of, we considered that a success of this function space approach. And what we did is we said, well, why don't we go full functional and try to understand the loss surface in function space rather than working with weights and biases, encouraged by their initial theoretical successes. And it turns out that in function space, understanding the loss surface in the overparametrized regime is actually quite simple. So consider here, on the left here, consider, actually there should be another picture here. Yeah. So here is an example of a neural network training with gradient descent. And there's an initialization here. We've purposely set up a bad initialization where the initial breakpoints are all away from the areas of high curvature, right? So we're setting up this neural network for failure, right? Gradient descent is not able to move the breakpoints where they need to go. So you see here what happened after it converged is it basically just did the best it could. Basically a local linear OLS type approximation in this region. In other words, gradient descent as a local optimization algorithm is not able to move the breakpoints into this region where it goes. So what happens? You get underfitting in that region. In this other region, you have way more breakpoints than you need. The individual value added of each breakpoint is nominal. You could prune a lot of the parameters associated with these breakpoints and not change the function. So this kind of mismatch of the breakpoint density with the curvature density in the function can cause problems for gradient descent. So in the overparametrized regime, so a lot of folks have noticed in deep learning that, if you overparameterize the network, meaning you have way more parameters than you actually need to express the function, that the optimization gets a lot easier, right? While still preserving generalization, which is, I'll talk about later. So from our theory work, it turns out that you can understand in the following way. So in this underfitting case, what happens is that you have a bunch of data points in each of these breakpoint intervals, right? So each of these pieces is defined by 2 consecutive breakpoints. So you have 3 points in this piece, 2 in this piece, and so on. In the overparametrized regime, where you massively increase the width, you have way, way more breakpoints than you need. But now what you've done to this partition of the input data on the x-axis is that you've over-partitioned it to the point where individual data points basically live in their own piece. Right? So I call these lonely partitions because every data point is alone. It's the only one in its piece, and there are many pieces that are just completely empty. So the space between 2 data points can have many, many pieces, many, many breakpoints with no data in them. And by the way, in high dimensional space, this problem is compounded. So it turns out, when you have a lonely partition, it turns out that we can prove mathematically that every such lonely partition is a critical point of the loss surface. And furthermore, that every lonely partition also admits a global minima. It's also, you can achieve a global minima, training loss of 0 with it. And you don't need to go to the massively overparametrized regime like the Aurora Du papers did, right? So we can be moderately overparametrized and still explain this overparametrization phenomenon. So the important thing here is that in function space, understanding the loss surface, understanding overparametrization becomes, in many ways, it becomes almost trivial. Oh, by the way, the one last thing I'll mention is that as you overparametrize, it turns out that the probability, right? So when you overparametrize, you're going to get the probability of these lonely partitions emerging in your data space is very high. How high is it? We can compute it exactly, and it turns out to just be the birthday problem. Right? It's the probability that 2 data points end up in the same bin, in the same piece. So it's just a birthday problem. So it's, again, trivial to compute the probability of being a lonely partition. So let's move to gradient descent. Now, gradient descent is the most difficult thing to analyze, even in function space. It requires quite a bit. So what we're going to do is we're going to talk about how to, what are the fundamental sort of laws, if you will, the dynamical laws by which breakpoints and slopes evolve. We're going to talk about why gradient descent is suboptimal in certain ways. And we're going to talk about the role of depth in easing some of the issues in gradient descent. It turns out that depth is not just about expressive power. In fact, we'll see that the expressive power afforded by depth is kind of nominal. It's nowhere near the theoretical capacity that you could achieve. But depth is extremely helpful for the optimization, it turns out. So we compute these dynamical laws. So remember, beta I is the breakpoints. mu I are these discrete curvatures or delta slopes, and yi hat is the function value at the ith training point. So don't worry about the details here, but basically we have dynamical laws that we can express the dynamics of the breakpoints and the delta slopes or curvatures in terms of the residuals and the data points. Right? So we can write down these laws, and they're tractable enough that we can prove the important things that we see empirically. So the first thing I want to show you is that I alluded to earlier in the talk, a mismatch between the breakpoints and the curvature in the function very quickly leads to suboptimal fitting. And not just in these extreme cases, even in regular cases where you have a normal initialization. So it really does lead to suboptimality in many cases, underfitting locally. The key issue is that oh, I can't control this. Yeah. The key issue is that you notice these breakpoints don't move very much, right? And that turns out to be due to the loss surface. There are so many local minima, as I showed you, at least high degree polynomially many. In the overparametrized case, there are exponentially many local minima. There's so many local minima that the breakpoints don't have much room to move around. So one thing you could do, so now how can we rescue this? How can we solve this? Is there some simple way, some simple new learning algorithm that we could develop by just taking this empirical fact and trying to reduce the difficulty with it? So what we do is very, very simple, right? Is to say, let me take some of these low value added breakpoints and let me move them around. And I can use this reparametrization because I can go back and forth between the neural network parametrization and this breakpoint delta slope parametrization. I can say I have a desired distribution in beta, and I can induce the set of weights and biases. I can invert to get the set of weights and biases that will achieve that distribution. And when I do that, you can actually show that, compared to a standard init, if I try to say initialize with a uniform breakpoint density, the uniform in the x-axis here, that I can dramatically reduce the amount of test loss and training loss. So it really eases the optimization quite a bit with these simple tricks. And more broadly, there is a lot of room for data-dependent initializations, both based on prior knowledge or just based on fast approximate statistics of your input data that could dramatically help gradient descent in many cases. So here's in a simulation where we do this breakpoint relocation. So you see new breakpoints will emerge. So in this case, what we've done is we call it breakpoint relocation, where we basically take low value added breakpoints and reallocate to the areas of high residual error. And you see that very quickly it eases the optimization quite a bit compared to the local minima you would have achieved otherwise. And you can see the training loss here. The training loss equilibrates, and then you reallocate a breakpoint, and then it drops and equilibrates and so on until you get to the end here. So very, very simple modifications to the breakpoints, kind of common sense, obvious in function space modifications can make a big difference to the optimization.
Is it easy to figure out what modifications of weights and biases will add a breakpoint at a particular point?
Yeah, so going back and forth, the reparametrization between the two, it's not easy, but we're developing fast algorithms to do it. So yes, there will be some computational cost to those algorithms, but basically you wait until gradient descent converges when you've squeezed all the juice you can out of it, and then you make one of these global moves using this. So there's going to be a cost training loss trade-off, but by the time you get stuck here, it's worth it for you to try something different. Right. Yes?
Is this stochastic gradient descent or?
This is full batch gradient descent, yeah. So I don't know offhand, yeah. We tried to keep everything as simple as possible to begin with, and then add one trick at a time to try and understand what it does. We have not explored much with SGD yet, or dropout. But in high dimensional problems, both SGD and dropout serve as regularizers, and they also, SGD in particular, does help escape saddles. So there will definitely be some effect there. So just how suboptimal is gradient descent? We don't really have any other algorithms to compare gradient descent to. Everything is a variant of gradient descent, right? Well, it turns out in low dimensions, it turns out that there are globally optimal algorithms that exist for one-dimensional piecewise linear and continuous piecewise linear regressions. So these globally optimal algorithms are actually a dynamic programming algorithm. So the dynamic programming algorithm basically assumes that, suppose you have the optimal partition with the breakpoints for a particular function. It turns out that the optimal partition is itself composed of optimal subpartitions, right? And that key fact can be exploited to write down a recursion relation, and then that leads to the DP algorithm. So this very, very fast DP algorithm has been known for decades. It's used a lot in econometrics and statistics. And recently, Ludwig Schmidt and others at MIT and Berkeley developed a very, very fast version of this DP algorithm called greedy merge, shown here in green. So we said, well, let's just, in this one-dimensional case, we can actually compare gradient descent to these other algorithms. Let's see how bad is it, right? So we tried 13 different function classes with a variety of different, very, very high curvature, continuous piecewise linear, random, all kinds of different function classes. We sampled randomly from them, and we trained all of these different algorithms on them and tried to do a systematic comparison. And what we find is that as you increase the number of pieces, so here you have the number of pieces on the x-axis, the training loss you achieve, conditioned on the different algorithms, you see that all the gradient-based algorithms kind of have this kind of linear, this is a log scale here, they have a kind of a linear drop, whereas the greedy and the greedy merge, the DP and the greedy merge, they have a really easy time. They very, very quickly, for a very low number of pieces, are able to optimize this, right? So gradient descent is a really, really bad optimization algorithm. And the optimization folks would probably tell you this years ago, but they just couldn't find an alternative. So one line of future work that kind of comes out from this function space view is, how do we scale greedy merge or the DP algorithm to high dimensions, right? And more broadly, we still want to use gradient descent in high dimensions, even though it's statistically suboptimal, because it's really fast, right? So there's this computational cost associated with the DP algorithm that is not, gradient descent is a lot faster in high dimensions, right, per iteration. So there's this interesting trade-off that has to happen between using a statistically suboptimal estimator, i.e. gradient descent algorithms, but way, way faster per iteration cost. In the limit of very, very large amounts of data, which is where we find ourselves today, it makes sense to use gradient descent, and then every now and then when gradient descent gets stuck, switch to a more costly but more accurate global algorithm, right? So I believe strongly that the future of learning algorithms will still be based on gradient descent, but we will stop when we get stuck and switch and make some global moves that are more costly but will get us out of these local minima. Yes?
So you're probably aware of them, and I want to know whether you want to say a few words. But there are the first order methods, accelerated first order methods, which achieve almost the rate of the second order with only gradient.
For which kinds of problems?
I don't know for neural network, but in general, like heavy ball algorithm, the Nesterov acceleration, the last 10 years have been very productive.
Yeah, so
all of them are almost second order.
Yeah, so the problem here though is that it's still a local algorithm. So Hessian, using the Hessian is not going to save you here, right? Because there's so many local minima. So these algorithms, this DP algorithm and this greedy merge algorithm, do not use any gradients at all. They're global.
Okay, so
yeah.
Okay, so
yeah.
then it's not linear versus quadratic. It's more.
Yeah. The quadratic will help you a little bit, but it won't get you this. Yeah.
Okay.
Yeah. So these are globally optimal because there's this recursion relation you can take advantage of. So in fact, in many ways, you don't even care about the loss surface with the DP algorithm. This hybridization, yep.
So, but you referred earlier to this idea that SGD is an implicit regularization also, right? Which we're lacking if we go to this, and whether do we actually want the optimal that the DP would give us if we could get it?
Well, so what we find is that these solutions, at least for all the functions, that they also generalize well. The DP and the greedy merge solutions generalize extremely well. That's what we find so far. But this is for the 1D function classes that we explored. So with high D, let's see. But remember, in 1D, we can control the curvature. So we try some really, really hard function classes that are way more complex than even the CFAR or the ImageNet functions in many ways, right? So, but the jury is out. We'll see when we scale to high dimensions. We'll see what happens. And remember, I'm saying that we still, in high dimensions, the speed, the wall time cost and the speed of gradient descent means that it should be a part of any algorithm. But when it gets stuck, we should have an alternative, a choice to make some global moves. So I don't think we will be able to scale these global algorithms entirely by themselves. I think they will serve as a choice within the larger algorithm. Okay, so this brings up I talked earlier about the value of depth. We all have this belief that depth is all about expressive power, right? Most of the theoretical results show that as you increase the depth of a neural network, the number of functions that you can express, in principle, grows exponentially in that depth. But it turns out that not many folks had actually tested this empirically, right? So you have a theory, you got to test it. You don't have to tell the physicist that. Nobody had actually tested this in actual real neural networks until recently. So there's a paper from Hannon and Rolnick this past year, which basically tried this out on MNIST and CFAR10 trained networks, and they computed the number of pieces in the underlying functions. And they found that the number of pieces, a measure of the complexity of the function, was way lower than the theoretical upper bound possible, right? The other thing they found, surprisingly, was that as you increase the depth of the network, the number of pieces it can express was not a function of the number of parameters. Instead, it grew with the number of hidden units, the total number of neurons in the network. Another surprise. So they had these findings, these surprising findings in their recent work. And so what we set out to do is say, can we reproduce these in these simple 1D examples? Do they still exist? And it turned out that yes, we could. We find that the number of pieces induced in simple, shallow, and deep networks for univariate functions scale with the number of hidden units, and that they're nowhere near the theoretical maximum that you can achieve. And again, it comes back to gradient descent. The way gradient descent is able to change parameters, it does not allow it to achieve the full expressive power afforded by the architecture. So gradient descent is your learning bottleneck. It drastically reduces the expressive power of your architecture. It's the bottleneck. So if depth is only sort of weakly responsible for expressivity, but we see in deep learning that depth gets us to the best generalization error, time and time again, we find that depth helps us. What is depth really adding? At least in this specific case of these fully connected deep ReLu networks trained on univariate functions, what we find after developing some visualizations to really see what's going on under the hood, what we find is that it seems like it's much more about the ability to move the breakpoints around. The minute you add a second hidden layer, a third hidden layer to a network, it turns out that the mobility of the breakpoints increases dramatically. I'll show you some evidence of that. But briefly, here's this visualization we've developed, which at each hidden layer allows you to see the breakpoints induced by every hidden neuron in that layer. So hidden layer 1, 2, 3. And each of the breakpoints is color-coded by its layer. And then you can see it here in the global view of the effective function that neural network is approximating. And you can see the dynamics here of how, and so you notice that not only can the breakpoints move way more than in the earlier simulations I showed you, they also disappear and they're basically created and annihilated as well. So a breakpoint can annihilate, disappear, and then show up somewhere else. So now you don't, before in the one hidden layer case, a breakpoint, the number of breakpoints is fixed. In the deep case, the number of breakpoints is no longer fixed. It is a function that can vary over time. And indeed, gradient descent takes advantage of that. So when you have a much deeper neural network, the ability to create, annihilate, and migrate breakpoints with higher velocity allows you to achieve a much better optimization. But it's not about the expressive power. It's really about the ease of optimization. And by the way, the definition of what is an active breakpoint is a bit subtle for a deep network. For a shallow network, it's trivial. But for a deep network, it's quite subtle. So I won't talk about it now, but if anybody's interested in that, we have an appendix in our paper. And it's kind of we have to formalize, be very careful in order to get the actual number of active breakpoints. There are many breakpoints that are induced that are not active, meaning they don't contribute to the function. So, anyways, I showed you this. Yeah. So if we can make this quantitative, we can look at the breakpoint births and deaths and the breakpoint velocities by layer, and indeed we find that compared to shallow networks, the velocity is much higher, and of course, there are no births and deaths in shallow networks. So, creation annihilation is important here. By the way, it's also kind of cool that when breakpoints are born, they always come in pairs. So you have like an electron, positron, and then when they annihilate, they always annihilate in pairs. So, fun analogies with physics. So finally, regularization or generalization. Yes.
ResNets are very popular now, which seems like they could easily tie into how breakpoints are created and destroyed. Do you have any?
Yeah.
Is there any work in that area yet?
Yeah. I can talk to you about it offline. We haven't published it yet. We haven't submitted it yet, but we have ResNets have a big impact on the breakpoint structure and on the spline structure. Yeah. So we can talk about that. Yeah. So let's talk about generalization. So, there are various theories running around about what is causing this implicit regularization. They usually focus on the high-dimensional problems, which are, of course, very difficult to understand because we don't even know what the ground truth function is. So what we did is said, let's set out with these simple problems, and let's first completely understand what's going on in these simpler settings. And what we did is, first we said, what is the impact of the initialization on this regularization? So there's some theories floating around about it's not just about the dynamics of the optimization algorithm, that actually our particular initialization is also really helping with regularization. So we decided to test that systematically in this setting. So what we did is that we generated random continuous piecewise linear functions with many pieces, shown here in orange, and we initialized our neural networks to these random functions. Now, the standard initialization is shown in blue, and by our earlier theory, we know that it's extremely smooth. The curvature is very low at each breakpoint. But this is unlike any standard initialization. So we asked ourselves, what would happen if we initialized neural networks this way, all else equal, leave the rest of the optimization algorithm untouched? And here is the final at the end of training when it's converged. You can see that the blue algorithm converges to the ground truth, which is in this case also a CPWL function. But the sort of spiky initialization, really all the spikes are still around at the end, even at the end of convergence. So the spiky inits are remembered throughout training by the gradient descent algorithm, and they significantly increase the generalization error. Remember, both of these have a training loss of 0. Both of these are global minima. They interpolate the training data perfectly, but the generalization error of the spiky init is terrible. And by the way, if you wonder if maybe going deep might help, it can help a little bit. So it smoothens out some of the spikes, but overall, it's still, the generalization error is poorer, all else equal, with the spiky init, or less smooth init. So what this means is that, and we quantify that across many different function classes, shallow versus shallow standard, shallow spiky, deep standard, deep spiky, and you can see that indeed there is a strong, the init matters quite a bit. So this, we kind of got lucky in many ways. The random inits that we designed in deep learning, which were all about making sure that backprop didn't blow up or that it didn't vanish the gradients, right? We designed the inits according to that criterion, and it turned out that that led us to very, very smooth inits, which also happened to be really good for generalization. So get lucky. That happens a lot in deep learning, right? You find a trick, you come up with a rationalization for it, and then later on, a paper comes out that more systematically studies it and figures out that it works for a different reason than you thought. Okay, so that was the impact of the initialization. The other big factor that is posited in the literature is this overparametrization, right? So the width of the network. The wider, one of the most mysterious phenomena in deep learning is that the wider you go, many cases you get better and better test error, right? Which is an unheard of phenomenon in general, right? It kind of violates basic laws of machine learning. So how can you have way more parameters and generalize better? So what I want to show you here is what happens when we try to train to match a very simple function here. It's a piecewise linear function, the two green lines, and there's a data gap between the two. This is to model the fact that typically you have a lot of space, empty space between your training data points. And we're going to start with a width of 20, 40, and 200 units. And I want you to watch and see what happens both in time and as a function of width. So you notice that the area between the data is actually quadratic. It looks smooth. All of these will achieve a training loss of 0. But you notice that the one that has more hidden units has a smoother curvature. So this is the implicit regularization phenomenon as reproduced with 1D functions. The more hidden units you have, the more the curvature is flattened out, smoothened out. And remember, the training loss could care less about this gap. The training loss is mean squared error over the training data, and the only training data is in the two lines, right? And yet, obviously, the area between the gaps is very important for generalization. So this is a very simple reproduction of this larger phenomenon in low-dimensional functions. So now let's try a little bit harder function. Let's try or not necessarily harder, but just different. Let's try a function that's underlyingly smooth. So a quadratic function, the simplest function that has non-trivial curvature. Let's try that and see what happens. And from left to right top, we're going to have the least number of hidden units, 10 hidden units, and here we have 160 hidden units. So again, all of these achieve a training loss of 0, global minima. But notice, if you only have 10 hidden units, and thus at most 10 breakpoints, versus 160 here, notice that the gap, the area between, in the data gap, this one smooths out the function, whereas this one is still, it's non-differentiable, right? So it seems, just by looking by eye, it seems that as you increase the width, you're getting this smoothness for free somehow. Now try it for a sharp target function, meaning a function that is underlyingly continuous and differentiable, but has a very sharp first derivative. See what happens there. So again, the training loss will be exactly 0, so we've achieved a global minima. But in the low width case, you have basically a piecewise linear approximation, highly non-differentiable. Here, if you zoom in, here you'll find little quadratics, little cubics. So it's smoothed out the area. Okay, so what is the, and if we quantify this, again, quantify this across different hidden units and measure the so-called the smoothness of the function, we see that in this case we're measuring roughness, so lower is smoother. We see that as you increase the number of hidden units for the underlyingly smooth or underlyingly smooth and sharp function, you see that the roughness decreases, or equivalently, that the smoothness increases in the data gaps. This is just smoothness in the data gaps. This is what's relevant for generalization. And furthermore, back to the as you vary the distribution of the initial weights, the variance, which controls the smoothness, you get more and more roughness, right? So if you make the initial function less smooth, then you get higher and higher roughness in the final function. So both of these factors matter. So after doing these empirical studies to kind of systematically figure out what matters, we then sat down to try and use our laws of breakpoint and delta slope curvature dynamics to try and prove what's actually going on. And so these are the laws, again, reminding you from earlier. And when we use these laws, it turns out, again, in function space, there's a very simple proof of what's going on in these settings. So you write down the dynamics of the curvatures of the delta slopes, and they satisfy this particular law for each breakpoint I. You vectorize it, so you get this. You get these vector dynamical equations. Notice that the right-hand side here, the gradient, weakly depends on I. In fact, it only depends on each individual breakpoint through the orientation or sign of that breakpoint. So you have a very weak dependence. So in other words, if you're in the data gap, if you're a breakpoint in the data gap, all the breakpoints basically have very similar gradients. This is why I factor out this scalar here, and the rest is all one vector in all these breakpoints. And then the critical thing is when you overparametrize, when you increase the width, you can take a continuum limit, right? Take the limit as the spacing between the breakpoints goes to 0, and you get this continuous space-time representation of the curvature as a function of x and t. And furthermore, the dynamics, you can solve it in terms of the initial condition plus these extra terms here, an affine. This initial condition right here, this is the initial smoothness of the function. So the initial condition matters a lot for the final curvature. So here we plug in the init smoothness, so basically this is very close to 0. And we have this term left, this affine term. Notice that these two terms come directly from these two, which come directly from these two. So we've got this affine function that represents the curvature at convergence. Now we integrate twice in x. And of course, when you integrate twice, the constant coefficient and the constant and the linear term become cubic, quadratic and cubic. And you have an extra two terms here that implement the boundary conditions. So notice our approximation of our function f hat is a cubic, even though the deep ReLu network is a continuous piecewise linear model. Another way to say this is that the training loss only cares about matching the data, and that can be done just by using these two coefficients, C0 and C1 here. You can use those to set to match the 0th and first derivative of your ground truth function. However, these two extra terms are a surprise. We did not expect these. And so these terms are, quadratic and cubic, and they implement the matching. The matching, instead of being a pointy matching, is smoothed out. So not only if you do this, you get 0th and first order derivatives matching. If you do this, you get second and third order derivatives matching. So it's these terms that we did not expect. We didn't put it into our parameterization explicitly. They emerge because of these dynamics, because of the very smooth init, and because of the overparametrization. We take a continuum limit, and because of this discrete curvature-based parameterization. So it's a combination of three factors, none of which we did on purpose, that leads to this quadratic and cubic terms, and thus the smoothing. Yes?
Can you do this for the dynamics on the breakpoints that's induced by gradient descent on the weights biases?
I didn't quite follow. You're saying?
So you're talking about if I do gradient descent on the breakpoints and the curvatures?
No. This is This is gradient descent. I put the wrong equation here. Yeah. So this is actually supposed to be the equation. You do gradient descent on the weights and biases. You re-express it in breakpoints and slopes. But you're right. I put the wrong dynamics here. It's a slightly different. The equations have the same terms, but they're different multipliers in front. But yeah, you're right. This is the equation for the dynamics if I were to do gradients with respect to the breakpoint delta slope parameters.
So
Yeah.
For either gradient descent, you get that.
You get this same kind of term, except the multipliers in front change slightly. Yeah. Yeah. So this is the so this is. We believe that this explanation, which currently holds only for these simple, we believe that this should scale to high dimensions, but that's ongoing work, and so we're kind of next steps is to really explore this in high dimensions to see is this still responsible in high dimensions. Okay, so I will. I don't have much time, but I just want to show you what happens based on this function lens. We now start developing new probing tools, and we start looking at the same questions that we've been obsessed with in deep learning. One of them being, what are all these adversarial examples? Why do we have these adversarial directions in our neural networks? And I want to show you that with this new lens in mind, you can start asking different questions. You start probing different observables, and you see very interesting things. So in the context of adversarial examples, what we did is we said during training, this is for a real network trained on CFAR 10. In a real network, I can ask between a data point from one class and a data point from an adversarial class, I can look at the logits along the line between the two data points, and I can ask, how does that change during training? And furthermore, I can say a random direction versus an adversarial direction, what is the difference? And it turns out there's a massive difference in the number of breakpoints and the amount of curvature in these directions. In a random direction, the function is very flat. And that's because of the very flat initialization. But in these adversarial directions, the curvature is actually 10 to 20 times higher in terms of number of breakpoints. And you see that it starts flat and it grows. So these adversarial directions are, it looks like they're actual directions of real features. This is what real features should behave like. So just, so anyways, the point is that with this new function lens, a variety of things are possible. One, we can start to get some more theoretical understanding of many of the important unexplained phenomena in deep learning. Two, we can develop new tools, right? This is where I think it would be very useful for the physics community to be able to visualize and then probe their neural networks. You have so much prior knowledge. You can do a lot of sanity checking. Three, you can develop new architectures, inits, and algorithms, again, because you have so much prior knowledge. And so this is some of our future work, and thank you all for your attention.